So who am I? My name is Maddie Stone. I am a reverse engineer on the Google Play Protect team under Android security, and I've been there for about a year. Before that, I have about 5 years of experience doing hardware and firmware reversing and exploit dev. So, why do we even care? What is the whole point of this? Where are we coming from? So the reason why I'm talking and wanted to focus on anti-analysis techniques was very first off, the reason they exist is this whole sort of dynamic between us as malware analysts and the malware developers. And so we're both striving for asymmetric advantage, so they want to be able to create malware that super quickly, that has the most market share, that they're accomplishing their goal, while we want to be able to detect it that much faster. So that's this mindset that we're coming from of they can create anti-analysis techniques, but can we detect them and prevent them and get around them with less investment than it takes for them to develop them. So what is this anti-analysis technique? Basically, just to make it harder for you to figure out what they're trying to hide. So that this is going to encompass all of anti-reverse engineering, anti-debugging, anti-emulation, all of those things I'm packaging up into anti-analysis. So let's take a step back and set the context. What's the story? Where are we? On the Google Play Protect team, we have so many apps coming in all the time, and certain ones are flagged for a human reviewer. When that's escalated to me, I want to take a look and decide as quickly as possible, is this benign or is it malware, and should we start issuing warnings? So this app came up. It looked pretty normal, but there was one interesting thing. It had an ELF file embedded in the APK that it didn't look right. I couldn't tell if it was actually malware or not yet, but I also noticed that there were at least 100 other digests or APKs out there that also included this ELF library. So that got me in this mindset of, one, I need to decide very quickly whether this is malware or benign, so that we can get protections out, but I also need to figure out why all of these different APKs are using it. So if you're sort of new to the Android malware analysis, we have our APK, that's your Android application, and in there you'll usually see it's mostly running on the Java code, which you will find in classes.dex. However, developers can choose to write and have functionality that is also in the C or C++ compiled code, and that's what we're talking about today. One of these ELF libraries, a shared object, that is embedded in the APK and has the native functionality. So, what are we talking about? We are going to talk about the wedding cake anti-analysis library, which is this native code. And why wedding cake? It's because it's got lots of layers. So we're going to go over all of these different layers, why it's so robust, what makes it so interesting, and how can you reverse engineer it more quickly, and what would I have done instead of falling for each of their traps along the way. So, once again, why wedding cake? Why is this interesting? So since doing this research, I have found at least 5,000 distinct APKs in the wild that contain wedding cake. None of these samples are benign. All of them are malware. And one of the most notable aspects is the newer variants of the Chamois Android botnet family, which this links to when the slides are posted, a blog post we did about it before, is using this to hide their functionality. So what wedding cake is it wraps the functionality that the malware authors are trying to hide. So this diagram came from the initial blog post about Chamois in late 2016. So what we're going to focus on is stage 3, which is the ELF there. So that's what they had studied, analyzed back then. What's new is now you see this wedding cake packed jar. But once I finally got through all of the anti-reversing and anti-analysis techniques, the decryption and everything we're going to talk about today, what I found was I had just unpacked the packed Unpacker, because that's what stage 3 was. So I was able to then say, yes, this is a part of this family, and I now know that these signatures of this ELF, which I've now called wedding cake, just wrap everything else. So what are all these different techniques that we're going to talk about? What makes it so interesting? First, one of the things that's interesting is previously in Android, what we had seen is generally if someone was going to implement anti-analysis, anti-debugging types of techniques, they were usually still in Java because that's what the malware developers were already using. It sometimes has a lower point of entry than C or C++ compiled code. So the first notable thing was that all of this is in native code. First, we're going to start about some of the JNI, or Java Native Interface manipulations. Then we're going to go into some places where they've used anti-reversing techniques, in-place decryption, and finally to about 40 different runtime environment checks that they use. So none of these in and of themselves are super novel, but the fact that they embedded each one in each other is what made it so complex and difficult to both signature, reverse, and understand what was happening. So what's the characteristics? How can you notice if you've seen it or not? Very first thing is that, as we've said, it's an ELF or .so file in the APK. Usually it is 3 to 8 random lowercase letters is how they've named it. Probably not after this talk, but you know. So the other thing is that the Java code that has to interact with this native library, it is always random lettered class names as well. So what that also tells us is that this is distributed as source code, and so it is dynamically generating the class names and the library names every time they build the application. Lastly, 2 things you can look for, but probably not in a couple of weeks anymore, are these 2 strings in the comment section of the ELF. A few more of the more key characteristics of wedding cake is that there is always 2 native methods that are declared in the Java application. So we're going to go over a bit how the JNI works and how execution is passed from the Java code into the native code, but what you'll see is that there are always these 2 functions, and there's sometimes this third depending on the sort of version and when they compiled it. So the main function or method that we will talk about that they implement in the native code is here called VXEG, again dynamically generated at compile time, but this is going to be the function that performs all of our runtime environment checks and starts that main functionality of the ELF that the malware author was trying to hide. In every version though, you will see that they have these same method signatures. So for example, VXEG returns an int and takes an object array as the arguments. One of the other interesting things I found as I really tried to understand all of the different variants and how all these different samples were using it is that there are many different CPU variants of it. So the most common is in most of the Android ecosystem is the 32-bit, what they call an Android generic ARM. So that uses a CPU keyword ARMY ABI. But I've also seen version 32-bit ARM v7, ARM64, as well as x86. Here is a link to VirusTotal and a digest for one of the APK samples that includes 3 of these different CPU variants in it. And what's really interesting and what we can talk about and keep in mind going through the rest of this talk is that every single one of these different CPU variants has the same functionality. So that's not changing across any of them. So let's start analyzing. This is the sample that I have used as sort of walkthrough. If later on you're interested, it's up on VirusTotal as well. So you can look into it and follow along later when I post the slides if you're interested in that. So first, what is JNI? How do Android apps even use native code? So basically Java native interface. In your Java application where execution has to start in the Android app, you can declare that you have methods that are implemented in your C or C++ or other compiled code. So you just declare it as you see here, native keyword, there's nothing else in that method. Then you just write it in C or C++. But the JNI interface has to actually know how to pair these 2 things. And it has to know where to look for these methods and where they might be implemented. So the very first thing you'll have to do in the Java side of your, or Kotlin, of your Android application is load into memory that native library. So you have two options, both basically perform the same thing, system.load_library or system.load. The key thing to remember as we get into the disassembly of the ELF is that when either of these two methods are called in Java, that calls the exported method in the, or exported function in the ELF called JNI onload. So this is gonna become really important later in our analysis. So now you've loaded this into memory, but how still is this JNI going to understand that this Java declared method is going to match up and run this native method? There has to be some way to pair and know that these two things go together. So you have two options. One is discovery, where in your compiled code, the method or the implementation of the method, so the function there, is named Java underscore the mingled class name underscore the mingled method name. This is really nice because it's a really easy indicator to look and find in your ELF if you're trying to pair and understand what's being run when that Java native method is called from the application. The second option that developers can use is using the register natives function. So this, you don't have to have any of your functions named in the ELF, but what you will still have to use is a string of both the method name and the method signature, so they know that this function that is in the compiled code is what is run when you call the Java native method. So this is what register native signature looks like, and what the key we need to remember is that it requires this string, or the char array, of name and the signature. And what I mean by signature in this context is here is one of our Java native declared methods. So if it was returning a string and taking an integer as an argument, then you'll have the I in the parentheses and then the type that's being returned at the end. So these are really easy things to identify when you have your ELF. But when I opened up the library that was in my sample to start, I didn't see any of this. There were no strings, none of the functions were named. It didn't even have JNI onload declared in the function. And what this was is that in every disassembler I've opened, or every disassembler I've tried this far, including IDA Pro, when you try and look at the code that is labeled as JNI onload, IDA was not able to define it as a function due to these two blocks of data. So that is another really strong indicator and signature when I've been able to open it up, because this has been true of every different sample that was compiled in 32-bit ARM. So first thing you gotta do to figure it out is super easy, just declare it as code, you have your function. But now where do we start? Because we wanted to focus our analysis on those Java declared methods. They were declared for a reason, we see them called in the Java code, yet we can't find what is actually implemented to be associated with those methods. Because they should either have a native function here in the ELF with that mangled Java name, or they should have the strings of the signature and the name for register natives to run on it. So where I decided to start was JNI onload, because before any of those native methods could run, you still had to load the library into memory. And when I started looking at JNI onload, it had all of these repetitive calls to the same function at the end, and it was taking in arguments of different blocks of memory. So this is a really, really strong signal of encryption, or decryption, because you have to run the decryption function over different places, and then hopefully we'll have more information about how this works. So in this case, all of the yellow blocks are the calls to the same function, sub to F30. I highlighted one of them, and that's gonna be what we believe right now is our decryption subroutine. So that's the next place to start, because obviously I want to understand and be able to analyze this library as it runs in memory. So go ahead, figure out, put the different arguments in there. It takes 4 arguments each time it's called. First, the pointer to the encrypted bytes, the length of those bytes that should be decrypted, and then it has 2 arguments that stay the same the whole time. We have a word seed array, which is an array of 4 bytes of each value is 4 bytes, and then a byte seed array. So these are generated before any of the decryption calls start, and then the same things is passed each time. So this is the IDA generated decompiler, which I sort of cleaned up a little, of what the seed array's functions were. I went through this, tried to understand it, coded up a super simple thing in Python to go ahead and generate it so that I could see what those values were. And what I found is that they simply were allocating 2 arrays from 0 to 255. So they wrote this complex algorithm instead of 2 lines to allocate these arrays. So this was a first technique and a really great use of my 6 hours as I was coding it up and trying to understand what it was doing. So what I would suggest in the future is that, and what I would do instead, was just run it dynamically and grab them. I already knew the same values were passed each time. They weren't being regenerated, but instead I stuck with static reversing and fell for their anti-reversing trap. So hopefully if y'all see this algorithm in the future too, you won't fall for the same things, and I took the bullet for all of us. So we now have our seed arrays. We can move on to the decryption. The key and the overall framework of how the decryption works, since it's in place and it is running during JNI on load, so before the ELF is actually there in memory, is that the decryption function's called on that encrypted array of bytes. It does its decryption, and then it actually overwrites the encrypted bytes in the same place. So this gives us an idea of how to decrypt it in IDA, how we can start to analyze it as it would look in memory too. I personally was not able to identify it as any known encryption-decryption algorithm, but hey, if y'all can find it, I would be I would be very happy to know if you see it as something that you already know and is out there. So at this point, the key that I needed is I needed a solution that was going to work fast and be flexible. Because again, remember, I'm still trying to decide and make the decision, do we need to start alerting users, or is this benign and I can pass? And also I knew that there were at least 100 other samples out there, and each of them are compiled differently. So my key thoughts when going into this was that, 1, I don't need to fully understand the decryption algorithm. I just need something that's going to run over it and decrypt it for me so I can analyze the contents. The second thing I needed it to be flexible. Because I had so many samples, I didn't want to have to copy and paste, rewrite it, adjust for different memory addresses, different registers that are used in different places to develop my solution. So those are the 2 key things that I keep in mind whenever I'm trying to develop a quick decryption solution for these types of packed things. So I did open source my IDA Python script, and that is available there. You can also just Google IDA Python Embedded Toolkit, and it's under the Android stuff. I chose to use IDA Python because it is one of those, well, it's one of my favorite tools to use and where I'm super fast. And I also focused on translating the decryption to Python rather than trying to create true pseudocode or a code representation of it. What I mean by translating it, and this is how I play into the speed and move as quickly as possible, and is instead of understanding in the assembly what each of these registers do or what the developers might have called them or what their functions were, I just name variables in Python that have the same thing, and I run through and say a move is an equal, you can knot it, and just go step by step. Because that just allows you to follow along instead of trying to be like pattern matching and figuring out all the different aspects of it. One thing to keep in mind is that Python is obviously not a strongly typed language. Here in assembly, the instructions know exactly what size they're operating on, whether it's a byte, a half word, a word. So that leads to a lot of bugs if you don't keep it in mind. So if something's not working the way you're expecting, that's generally where I look. I also tend to write helper functions, which you can find and take in the script for anything else you want to use for a lot of the signed operations, since Python won't usually know that, okay, this is a byte that is operated on as signed or not. So let's do some demos and talk through this assembly. So this is our sample library. Oh, that's an interesting item view. Oops, okay. Well, we're not gonna look at it in graph view. So the first thing is, it's very small on the right, but there's nothing named Java, as we talked about. There's only all of the imported functions. So that's where we're pulling into our JNI onload function. And so that's what I'm scrolling through right here. Here is that decryption function that I already had showed you all the screenshot of. In each of the places that it takes bytes is they're all right after each other. It's a block of memory, and it's just random bytes. There's nothing that looks key or anything like that. IDA doesn't know, so all of them are declared as unknown data as we scroll through it. So when we look at our decryption subroutine, that one it will let me do. Here is the overall graph structure. So what we have is 2 while loops. There's one at the top and one at the bottom. And so when you're doing translation for that, of those translation to Python in order to just have a solution that can run over it, I tend to find it's helpful to just, that's where you can have a variable that says keep looping true or keep looping it false, and you can just set that in the same way as your as the instructions did for like branch less than or not, branch greater than, and things like that, to sort of have that translation. So going through, is that large enough? The first thing I did was I coded up my decryption subroutine in Python, that translation we've talked about, and tested it over just one of the bytes raised to see, does anything come out of it? Am I doing this right? Are bugs coming up? And followed along. Once I understood that that decryption subroutine was correct, that's when I had to start thinking about the second problem, the adaptability. I have so many samples coming in, and I want to be able to compare them to each other. So I don't want to have to recode anything else for each new sample. I want something that I can run on anything and then be able to quickly analyze and check, does this decrypted library look like these others, or does something different stand out? So that means that I can't hard code in where those encrypted array addresses are. I can't hard code in what their bytes are. I can't know for sure where does this decryption subroutine live. So in my main script, where I start is first even just finding JNI onload. Just like as humans, that's where we started. That's where we can start with the Python script. I then went ahead and initialized my seed arrays. But the next job that the script needed to do for me was tell me where is each array, read its contents, and what is its length, because those are the two dynamically changing arguments to the decryption subroutine. So what I did was that I first wrote a subroutine called find decrypt sub, really creative, and went through JNI onload. So it starts about hex D0 off from the beginning of JNI onload, and then begins looking for repetitive calls using BL. Since that were in 32-bit ARM, I knew at the last chunk of the JNI onload function, they just repetitively call to this. So once I found a subroutine and used some string processing on IDA's disassembly, all I needed to get the disassembly, just using git disasm from the IDA Python APIs, I just did some string processing to see the address. I then just checked that that same subroutine was called at least 5 times to make sure, as a safety check, that I'd found the right subroutine. And then I recorded all of the cross-references, or the addresses that called that subroutine each place. Because every time they called the subroutine, they had to allocate or assign the arguments earlier. They had to say R0 is going to equal this pointer. So if I have those addresses, I can now figure out what's the encrypted array. So once I did that, I then iterated through each of those different cross-references. And every time I had a cross-reference, I would use regular expressions to look for the different types of instructions that could be assigning the encrypted array bytes, which are at the top of this thing. So you can always change that if you are looking at a different CPU of some sort. And then I pass it to this function called getArrayInLength. I do pass it the previously used length as well. And the reason for that is that there's a couple of different ways you can assign the length. If we look back, let's see if it's going to load. Yes. At JNI onload, first we see an example of where they assign the length here to R1 using this immediate assignment. Cool. But later on, they start storing that value on the stack as well, and also loading the length from the stack. Or sometimes they're using the same previous length. So accounting for all of those different regular expressions in those different cases is what I did within getArrayInLength. So finally, after that, we have a map of here is where the array starts, the encrypted array starts, and here's what its lengths. Then we can just thankfully use the IDA Python APIs and call to our decryption function, which we'd already tested, and then we get back the results of the decryption. And now, another reason why I like to use IDA Python instead of API is it allows us to just patch those bytes that previously were encrypted using the patch byte API and write them over that address. So now we are able to analyze our IDA database in the same way as it looks after all of this decryption has run in memory. So what this looks like is, obviously here we still have all of these unknowns. If we look at our strings, there's a lot of jumbled, but nothing really more. Oh, this is really small, sorry. So a lot of jumbled things, and then some of the common imports, exports in here, but nothing that really talks about that signature that we're still looking for, or the declared Java method names that we still need to be able to do that pairing from the beginning of our APK says, I have these native methods, what's run in this library? So when I run this file, script file, and then run our wedding cake decrypt, what we will see now back in our JNI onload is suddenly we have all these strings. So now we can start our analysis. Because one of those key things is, look, we have calls to dex class loader. We see a init. We see right here was that class name with all those jumbled letters. So now we can really start understanding what is this doing and getting past the decryption, and this script is going to run on all of our other samples too. Oops, where did my slides go? So, again, focus just on speed and flexibility. It's always hard for me because I like to understand everything I'm reversing, but sometimes it's not the right choice. If you are better at setting up ARM emulators or debuggers, then that could probably be a faster route too, but that would have taken me longer, so yeah. Oh, and one of the ways that I generally get around hard-coded addresses as well as registers is using regex. So just a screenshot, the top was all of the encrypted block of memory and then a segment where the same segment decrypted after running our script. And the key thing is now we do have that string of our function name vxcg. We have its signature, and now we also see in the structure the subroutine that is associated with it. So this is now where we can go. We can finally get to what we actually wanted to analyze in the beginning. The +1 at the end is just because it's running in thumb mode. So we have our 3 declared native methods. We know they're native subroutines that are run each time they're called. We have their signatures. Because each of them are named differently in all the samples, I just added a function number in the leftmost column to say that any of the native declared methods that have these same signatures would correspond in the same analysis as what I have here for vxcg or 2. So that leads us into our runtime environment checks, which I didn't know at the time. I just started my analysis on that function number 1. But what the goal of the malware developers was they wanted to understand if they are being dynamically analyzed, debugged, or emulated. Someone managed to get through probably the JNI manipulations, the anti-reversing, and the decryption. So now where are they? And they want to make sure this isn't a debugger that got around those things, or it's not some automated pipeline. And one of the interesting things that's sort of different and is changing with the evolution of Android and how there's not really the low-hanging fruit anymore is that they're willing to give up some of their market share as malware developers if that means weighting more heavily towards not being detected, which is not one of those things in a malware family such as Chamois, which is focused on making money through different types of fraud. What we saw here is that they're willing to not run on every device as long as they're not being detected. So, again, vxcg performs runtime environment checks, and there's 45 different ones of them. If any single one of these 45 checks fails, then we will stop execution of the app. So we're going to go through a couple different groups of these that make up the 45. The first one is going through all the system properties. So all of them are sort of aimed at being whether or not your hardware you're running on is an emulator or being debugged. And the first 37 checks they do are checking to see if the system property has a specific value. I obviously could not list them all here, so there is a link as well as in that IDA embedded toolkit where the decryption is of all 37 of these checks if you're interested in seeing what they're looking for. But most of them are based on looking for common emulators, debuggers. But one of the interesting ones too was they will not run if you do not have SE Linux in enabling mode. So that is one of the places where they're not going to generally run if your device is rooted and things like that. The last 5 that they go through is just checking if any of these 5 on the right exist, not even what their value is. And it's pretty clear why. They're all related to different types of emulators or things that emulators and debuggers set up in order to make it look like a real device. So the next thing they do is they want to make sure what architecture they're running on. They will not run if you are not running on ARM, which is really, really fascinating since we found x86 versions of this library too. Those x86 versions also include this check, even though they are running because you are on x86. So they don't do this with a clear API call. Instead, what they do is they open up /system/lib/libc.so and read the first 20 characters or 20 bytes from that file. This is still a part of the ELF header being the first 20 bytes. And then out of those 20 bytes, they only read 3 of them. The first check they do is for the byte that's at the eident EI class position in the ELF header, and that determines whether or not you're running as 32-bit or 64-bit. The last 2 bytes they do is what machine or hardware you are on. So in this case, they're looking for these values of either hex 28 or hex B7 to say you're either ARM or ARC64. So the only 2 combinations that are acceptable is 32-bit in ARM or 64-bit in ARC. If you are running anything else, then you exit and the application stops. The next thing they look for is to determine if Monkey is running. If you don't know what Monkey is, it is a tool that allows developers to emulate or pretend that a user is interacting with their device in their application. So, performing fake touches, fake clicks, and things like that. The way they go about trying to detect if Monkey is running is they open up proc. They then iterate through every directory. So after they open up proc, they check what each file or node's value is and whether or not it's a directory. If it's a directory, they check its name to determine whether or not it's an integer. And they then construct these two paths of the PID's directory for file for com, as well as command line. They read then out the max or a max up to 7F bytes, and then choose whichever one has more information. They then see if that information contains the Monkey package name at all. If it does, it means that Monkey is running and they choose to exit. So just a note, this doesn't work on anything Android N or Plus to open up proc and iterate through the PIDs. So in that case that they are not actually able to open up proc and PID, instead of exiting in that case, they will still just skip over that check and run. It's only if they're able to open do they exit if they see Monkey. The very last runtime environment check they do is to determine if the exposed framework is running as well. So exposed is a framework that allows you to hook or modify system code on your Android device. It's used on a lot of different forms for a lot of different reasons, but they want to make sure that you haven't hooked their app for analysis. So they're going to check if these two files are existing in proc self-maps, meaning they have been mapped into memory. And then if that one passes, they then also check using JNI find class methods if they are able to find either of these two exposed class methods are running too, because you want to be really sure exposed isn't running. But if you make it through all of those different 45 checks, as well as through the in-place decryption and anti-reversing, what I then found was it was code that I'd already analyzed before and that other team members had documented as well. And the sample I had been looking at was a new variant of the Chamois family, and it was just another Unpacker. So I spent, a couple of days, all my time focused on getting through this to unpack the packed Unpacker. But what was really interesting about this and what I had been thinking about a lot is one, they're willing, even though they're a large sort of money-making fraud botnet, and that's always been their goal, is market share, because that's how you make money, they had evolved to a point now that they were willing to miss out on potential targets if that means not being detected. And in addition, they were very intelligent in how they layered their anti-analysis techniques, because they targeted, one, I'm going to frustrate the human analyst through the decryption or the encryption and the anti-reverse engineering. Then they're also going to try and prevent dynamic static analysis, tools running over it to find strings or understanding of what was in the ELF. And lastly, they also are using techniques to detect if they are being dynamically analyzed. So packaging all of these together to try and target each of those different types of analysis that we all as defenders or attackers try to bring to the table here. So what I hope and what I was hoping to help or provide to you, and why I hope to have provided in the sense that you stayed until 6 p.m. on the last day of Black Hat, was some ideas of what is the current state of the art in terms of Android anti-analysis techniques, and how could you possibly get through them faster, things that you could look for, know that they're being used so you don't spend the same amount of time I did, and also, how can you write decryption solutions with the goal being fast and sort of agnostic to the exact sample you're looking at? And with that, thank you, and are there any questions?